Imagine a theory so powerful that it claims to explain everything from the smallest particles that form the fabric of reality to the most massive structures in the universe. A theory that suggests that our familiar three dimensions of space may just be the tip of an invisible iceberg. But what if this theory, despite its mathematical elegance, has never been directly observable? What if the most ambitious idea in physics remains a mystery to this day, even to those who created it? Venturing into the world of string theory, we explore hidden dimensions, unresolved paradoxes, and the ongoing search for the true nature of reality. What secrets does this theory hold? And why, after decades of research, is it still one of the most controversial ideas in science? In the summer of 1968, a quiet revolution began in the hallowed halls of CERN. Gabriele Veneziano, a young theoretical physicist, wrote a paper that, unbeknownst to him, laid the foundations for a theory designed to unravel the very fabric of the universe. Initially, his work was a modest attempt to explain the strong force, the mysterious interaction that holds atomic nuclei together. But soon, this work, entitled Construction of a Crossing Symmetric Reg Behavior Amplitude for Linearly Rising Trajectories, will resonate far beyond its original intent. The scientific community quickly realized the potential hidden in Veneziano's equations. Returning from a short vacation, Veneziano was surprised that his work had already generated considerable interest. It turned out that his model simultaneously solved several complex particle physics questions, which immediately made it a sensation. But at the time, neither Veneziano nor his colleagues realized they were on the cusp of something much bigger. A theory that was a radically new view of the nature of particles themselves. It took another 5 years before other pioneering theorists such as Leonard Susskind, Yoichiro Nambu, and Holger Nielsen revealed deeper implications of Veneziano's model. They began to piece together the idea that elementary particles might not be point-like objects, but tiny vibrating strings. These strings, they argued, could potentially explain the variety of particles observed in nature as different vibrational modes of the same fundamental entity. However, the first steps were fraught with difficulties. The nascent string theory struggled with several inconsistencies, not the least of which was the prediction of massless states, which contradicted the short-range nature of strong interactions. In addition, the theory required the existence of a universe with a more spatial dimension than the three we observe, a concept that, to put it mildly, troubled many physicists at the time. For most of the 1970s, string theory remained on the margins of theoretical physics. The field was dominated by the rapid development of the Standard Model, which successfully explained many particle interactions without requiring additional measurements or vibrating strings. Many scientists viewed string theory as an elegant but timely irrelevant workaround. The story was far from over. The beauty of the mathematics underlying string theory, as well as the persistence of a few dedicated researchers, kept the idea alive. And when the success of the Standard Model began to reveal its own limitations, for example, its inability to account for gravity, interest in string theory began to revive. The seed sown in Veneziano's 1968 paper grew by the end of the decade into a field that would capture the imagination of physicists for generations to come. So, string theory starts with a deceptively simple idea. At the most fundamental level, the universe is made up not of point particles, but tiny, vibrating strings. These strings are unimaginably small, much smaller than anything our current technology can detect. By vibrating, twisting, and folding into specific patterns, these strings give rise to the particles and forces we observe in the universe. Within this framework, the characteristics of each particle, its mass, charge, and spin, are determined by the particular mode of string vibrations. One of the key innovations of string theory is its ability to unify two previously incompatible frameworks, quantum mechanics and general relativity. Quantum mechanics describes the behavior of the very small, like atoms and subatomic particles, while general relativity governs the realm of the very large, including stars, galaxies, and the very fabric of space-time itself. However, the two theories don't fit together well. When physicists try to apply quantum mechanics to the gravitational force, the equations often produce ridiculous results, such as infinite values. String theory offers a potential solution by replacing point particles with strings that can move and interact in ways that avoid these problematic infinities. The elegant merger of the two concepts hints at the possibility that string theory could become the elusive theory of everything, a single theory that could explain all the fundamental forces and particles in the universe. However, the beauty of a string theory comes at a price. It requires additional dimensions beyond the usual 3 dimensions of space and 1 of time. According to string theory, the universe consists of 10 dimensions, 6 of which are compactified or curled up, so densely they're undetectable on our current scales. These extra dimensions are crucial because they provide the necessary space for the string oscillations that give rise to the variety of particles and forces we observe. One of the most speculative but fascinating implications of string theory is its prediction of the multiverse, a multitude, perhaps an infinite number, of universes that exist parallel to our own. Each of these universes may have different physical laws depending on how the strings in them vibrate and how extra dimensions are formed. At the heart of string theory is the concept of supersymmetry, a theoretical symmetry that suggests that every known particle has an undiscovered partner or superpartner. These superpartners can help explain why certain forces, such as electromagnetism and weak forces, behave the way they do. Supersymmetry also plays an important role in string theory because it helps stabilize the theory mathematically and allows gravity to be incorporated into the quantum framework. However, despite its promise, supersymmetry has not been observed in experiments such as the Large Hadron Collider. The lack of empirical evidence for both supersymmetry and the extra dimensions predicted by string theory has led some physicists to question whether the theory is a true reflection of reality or just a mathematically elegant construct. The bottom line is this: string theory, with its intricate predictions about vibrating strings and extra dimensions, has encountered a serious obstacle: a lack of empirical evidence. Unlike other theories in physics that have been confirmed by observation and experiments, string theory remains virtually untested, existing more as a mathematically elegant framework than as a proven physical reality. One of the most ambitious attempts to find evidence for string theory comes from experiments conducted at the Large Hadron Collider. The LHC, the world's most powerful particle gas pedal, was created to study the fundamental nature of the universe by colliding protons at unimaginable speed. Among the LHC's many goals is to detect evidence of supersymmetry, a crucial component of string theory that predicts the existence of partner particles for all known particles. These superpartners, if found, would provide strong support for string theory. However, despite years of searching, the superpartners were never discovered. The lack of evidence has led to growing skepticism among physicists. Critics argue that string theory may be more of a mathematical construct than a true description of reality. Its reliance on higher dimensions that are inaccessible to modern experiments makes it difficult, if not impossible, to test directly. This has led some to question whether the theory is at all provable, a key criterion for any scientific theory. Nevertheless, one of the most notable discoveries related to the theory occurred a couple of years ago, thanks to calculations made by physicists Pedro Vieira, Andrea Guerrieri, and Yo Penandones. Using a method known as the bootstrap approach, they calculated a specific number related to the quantum nature of gravity. Bootstrapping involves gaining new knowledge about the world by determining what's consistent with established facts. It's similar to a scientific way of solving problems using tools and knowledge already available. This number, denoted by the Greek letter alpha, represents the size of the first and largest quantum correction to the equations of Einstein's general theory of relativity. Remarkably, their calculated value of A in the 10-dimensional supersymmetric universe fully coincided with the predictions of string theory. The coincidence suggests that string theory may indeed reflect some fundamental aspects of quantum gravity. While this result does not confirm that the theory is the definitive version, it strongly suggests that it is still on the right track when it comes to describing the quantum aspects of gravity. In parallel with this experimental work, the development of advanced computational tools has led to significant progress in understanding the potential implications of string theory. Machine learning algorithms to solve the difficult problem of how the extra dimensions of string theory, the Calabi-Yau manifold, translate into the particles and forces we observe. Physicists like Fabian Ruhl and his colleagues used neural networks to approximate the metrics of these manifolds, an important step in determining how they can generate the elementary particles that make up our universe. This approach allowed the researchers to calculate the masses of certain particles based on the geometric properties of these manifolds, a significant step forward in connecting the abstract mathematics of string theory to the physical world. However, the debate has become increasingly heated over time. Proponents of the theory point to its mathematical neatness and its ability to provide a potential unification of all forces in nature that no other theories manage to do. They argue that the lack of experimental evidence is not a fatal flaw, but rather a reflection of the enormous challenges involved in exploring such fundamental aspects of the universe. Some even suggest that new experimental methods or future advances in technology may eventually uncover the hidden dimensions or particles that string theory predicts. However, this focus on mathematical elegance has its detractors. Critics argue that string theory's reliance on complex and unprovable mathematics pushes it into the realm of speculation rather than empirical science. They warn that the pursuit of this philosophy may divert resources and attention away from other promising areas of research that rely more on observable phenomena. This contradiction between mathematical beauty and empirical evidence led to a broader philosophical question. Is string theory a true physical description of the universe, or is it just a complex mathematical hypothesis? The lack of direct evidence and the difficulty of making testable predictions led to fears that the theory would never become anything more than an abstract intellectual exercise. While the search for evidence continues, the scientific community remains divided. The promise of string theory as a theory of everything hangs in the balance, and its fate depends on the future of experimental physics and the continued pursuit of a deeper understanding of the cosmos. Black holes, some of the most mysterious objects in the universe, represent a boundary where the laws of physics as we know them break down. At their core is a paradox that's puzzled scientists for decades, the information paradox. According to classical physics, when matter falls into a black hole, information about that matter is lost forever, seemingly violating the fundamental laws of quantum mechanics, according to which information must be preserved. String theory offers a compelling scheme that can resolve that paradox. Strings can encode information in a much more complex and subtle way than classical particles. Applied to black holes, the theory suggests that information that enters a black hole is not lost, but is stored in the strings that make up the black hole itself. This intriguing discovery is directly related to Hawking radiation, a theoretical prediction made by Stephen Hawking in 1974. He suggested that black holes are not completely black, but emit radiation due to quantum effects near the event horizon. This radiation, known as Hawking radiation, gradually causes the black hole to lose mass and eventually evaporate completely. However, Hawking's initial calculations showed this radiation was purely thermal. That is, it did not carry any information about the matter trapped in the black hole. This led to the alarming conclusion that after the black hole evaporates, all information about the objects trapped in it are lost forever. A direct contradiction to the principles of quantum mechanics. String theory offers a possible solution to this problem by suggesting that the radiation emitted by black holes may indeed carry information, albeit in a highly encrypted form. The idea is that the microscopic strings that make up a black hole can encode information about everything that enters it. As the black hole radiates and evaporates, this information slowly returns to the universe through Hawking radiation, preserving the principles of quantum mechanics. In addition, string theory suggests that black holes are not just astronomical objects, but also the key to understanding the fundamental nature of the universe. The study of black holes in the context of the theory bridges the gap between the microscopic world of quantum mechanics and the macroscopic world of general relativity. In this sense, black holes serve as laboratories for testing the ideas of string theory and exploring the connections between the micro and macrocosm. The insights gained from studying black holes in the context of string theory may eventually lead to a deeper understanding of the universe's greatest mysteries, bringing us closer to a unified theory of all things. As we move into the future, string theory faces both enormous challenges and unprecedented opportunities. Nevertheless, it's not without its competitors. Competing theories like the loop quantum gravity offer alternative explanations for the fundamental nature of the universe. Unlike string theory, which relies on these tiny vibrating strings and extra dimensions, loop quantum gravity attempts to quantize space and time itself, proposing that space-time consists of discrete loops rather than a smooth continuum. These competing concepts are pushing the scientific community to consider a wider range of possibilities in the search for a unified theory. This inevitably raises questions about the very nature of knowledge, the limitations of science, and the boundaries between what's considered empirical science and what can be considered mere mathematical abstraction. Kurt Gödel's incompleteness theorems serve as a profound reminder of the limitations inherent in any formal system of knowledge. Gödel showed that in any sufficiently complex system there's truths that cannot be proved within the system itself. This idea has philosophical implications for string theory. If the research for a complete and self-consistent theory of the universe is subject to the limitations described by Gödel, the question arises: can string theory ever truly realize its ambitious goals? The metaphor of the island of knowledge further emphasizes the limitations of what we can know. As our scientific knowledge expands, so does our awareness of the vast, uncharted territories that lie beyond it. String theory, with its reliance on abstract mathematics and higher dimensions, pushes the boundaries of this island, but also emphasizes how much remains beyond our grasp. The more we learn, the more we realize how little we really understand about the universe. This brings us to a key conflict within the scientific community: the tension between empirical science and mathematical theory. String theory, with its complex mathematical structure, has been criticized for its lack of direct empirical evidence. Critics argue that without experimental confirmation, string theory risks becoming a form of metaphysics, disconnected from the physical reality it tries to describe. Defenders of string theory, however, argue that the mathematical beauty and internal consistency of the theory justify its application, even in the absence of direct evidence. The controversy surrounding string theory echoes a broader historical pattern in science, where mathematical theories often precede empirical confirmation. For example, Einstein's general theory of relativity was initially accepted on the basis of its mathematical elegance, and then confirmed by observations. String theorists claim that their work is in a similar position, awaiting experimental tools capable of testing their predictions. And in fact, this is true. The future of string theory can only be determined by the availability of new experimental techniques. One such possibility is the development of more powerful particle gas pedals or gravitational wave detectors that could provide greater sensitivity. Moreover, ongoing research on black holes and their connections to quantum mechanics and string theory may yield crucial discoveries. As discussed earlier, the study of Hawking radiation, information paradoxes, and the role of strings describing the interior of a black hole is likely to remain fertile ground for research that could unlock some of the deepest mysteries of the universe. Looking to the future, we see that the scientific community remains divided as to whether string theory will ultimately prove to be the correct description of reality. What is certain, however, is that the path to a theory of all things will continue to drive innovation, inspire debate, and expand our understanding of the universe. Whether it's string theory or another system, the search process itself is what drives science forward, and the next few decades promise to be a watershed period in the history of physics that will finally bring us closer to answering the deepest questions about the nature of existence. Until then, stay tuned for those discoveries and breakthroughs that will shape the future of our understanding of the cosmos. Imagine a world teeming with the raw materials for life hidden among the stars. What if some of the most promising candidates for alien life dwell around the smallest and dimmest stars in our galaxy? Recent James Webb Space Telescope discoveries have revealed a hidden treasure: rocky, carbon-rich exoplanets orbiting tiny stars. These worlds may hold the secrets to the origin of life, offering conditions favorable for forming organic molecules. With its unprecedented sensitivity and advanced infrared capabilities, the James Webb Space Telescope has detected diamond-like carbon dust from the earliest stars in the universe. It is this carbon dust that plays a crucial role in the formation of stars and planets. But what makes these exoplanets so intriguing? Carbon is a fundamental element of organic chemistry, the basis of life as we know it. These planets may have all the conditions conducive to the formation of complex organic compounds, potentially lending to the emergence of life. And it's possible that around these miniature stars, where conditions are stable and long-lived, rocky planets with carbon-rich environments could be ideal laboratories for experiments with life. Should we reconsider our idea of where life might exist beyond Earth? First, let's talk a little bit about the basics. After all, life on a planet can't exist without the planet itself, right? The beginnings of planets and the essential ingredients for life they carry are found in protoplanetary disks, the huge rotating structures of gas and dust that surround young stars. These disks are the birthplaces of planets and the cradles of the complex chemistry that lays the foundation for the origin of everything in a planetary system, including the formation of organic molecules. Recent observations with powerful instruments like the Atacama Large Millimeter Array have revealed the presence of a rich diversity of organic molecules in these disks. These molecules, such as methane, formaldehyde, and acetylene, are formed by complex chemical reactions in the cold, dense regions of the disk. Collisions between gas and dust particles, combined with exposure to ultraviolet radiation from the central star and cosmic rays, trigger the synthesis of these crucial compounds. Organic molecules are extremely important because they represent the initial steps in the evolution of life. On Earth, simple organic compounds serve as precursors to more complex molecules such as amino acids and nucleotides, which eventually form proteins and DNA. The presence of these molecules in protoplanetary disks indicates that the building blocks of life may be widespread in the universe, forming naturally during the formation of planets. To better understand these processes, the scientists conducted laboratory experiments. With JWST, they've greatly expanded our understanding of the chemical composition of these disks. Its high-resolution infrared observations have provided detailed insights into the chemical processes occurring in the early stages of planetary systems. At the same time, a variety of key molecules, including water, carbon dioxide, and complex organic compounds, were detected, demonstrating the diversity of the chemical environment. One particular discovery made by JWST is the detailed mapping of the distribution of these molecules in the disks. This map shows how the chemical composition varies with distance from the central star, revealing regions rich in ice and organic compounds that are crucial for planet formation. The results suggest that young planets incorporate these organic molecules in ice during their formation, which may later contribute to a habitable environment. Understanding the chemical composition of protoplanetary disks expands our knowledge of how planets form and evolve. The presence of organic molecules and other complex compounds provide the necessary ingredients for life and suggests that the potential for life is embedded in the very process of planet formation. As these molecules are incorporated into evolving planets, they may be preserved in comets and asteroids, which can deliver them to the planet's surfaces through collisions. Chemical processes in disk are also indicative of dynamic interactions between the forming planets and their environment. For example, the movement and mixing of materials within the disk can lead to the formation of different planetary compositions and atmospheres. This chemical diversity is crucial for the creation of different planetary environments, some of which may also be favorable for the development of life. One of the James Webb Space Telescope's most remarkable discoveries last year was the detection of diamond-like carbon dust from some of the earliest stars in the universe. This unusual finding provides new insights into the processes that shape the early cosmos. JWST infrared sensors can detect the faintest signals from distant celestial objects, analyzing the spectra of light emitted by ancient stars. Scientists have identified signs of diamond-like carbon dust. This form of carbon is characterized by crystalline structures somewhat resembling terrestrial diamonds. Carbon dust plays a critical role in the formation of stars and planets. In the early stages of star formation, carbon dust acts as a coolant, helping the gas inside the molecular cloud to thicken and collapse under gravity. This cooling is necessary for the cloud to collapse and form new stars. As stars evolve and complete their life cycles, they eject carbon-rich materials into space, seeding the interstellar medium with the ingredients needed for the next generation of stars and planets. In addition to cooling, carbon dust contributes to the formation of solids in protoplanetary disks. These disks, composed of gas and dust surrounding young stars, are the birthplaces of planets. Carbon dust in such disks can stick together and grow to form the building blocks of rocky planets. The presence of diamond-like carbon dust suggests that even the earliest planetary systems may have had the necessary materials to form planets. The implications of this discovery extend to our understanding of the early universe. The discovery of diamond-like carbon dust in early stars indicates that carbon was abundant even in the infancy of the universe. This finding suggests that conditions for the formation of carbon-based molecules and potentially life existed much earlier than previously thought. Moreover, the presence of carbon dust in the early universe helps astronomers put together a timeline of cosmic evolution. It indicates that the first stars, known as population 3 stars, which formed shortly after the Big Bang, played an important role in enriching the universe with heavy elements such as carbon. As these massive stars lived and died, they ejected their carbon-rich material, contributing to the chemical complexity of the cosmos. Overall, a carbon-rich environment is essential for the development of complex carbon-based life forms. Although other elements and compounds also play an important role, it's the unique properties of carbon that make it indispensable for the development of life. And it is indispensable, of course, because of its unique ability to form stable, complex molecules. It can combine with 4 other atoms at the same time, creating a huge number of organic compounds essential for biological processes. This versatility allows the formation of long chains and rings that are the basis of proteins and other essential molecules, providing the complexity necessary for organisms to function. Even more intriguing and revolutionary is another discovery made with JWST in June of this year. A team of more than 40 scientists from around the world was able to peer into the protoplanetary disk around small stars. The study of ISO Chi 147, a young star in the Chameleon 1 star-forming region, found the richest menu of hydrocarbons ever observed in a planet-forming disk. Among them is the first detection of ethane outside of our solar system. The discovery of ethane is revolutionary because it is a key hydrocarbon that plays an important role in the chemistry of life. Ethane is a simple molecule that can act as a precursor to more complex organic compounds. These results suggest that protoplanetary disks around tiny stars are particularly effective at forming small, Earth-like planets rather than large gas giants like Jupiter. This is important because low-mass stars are more common in the Milky Way, indicating that there may be more terrestrial planets in our galaxy than previously thought. The protoplanetary disk around this star is characterized by a carbon-rich chemical composition with 13 carbon-containing molecules, including ethane and benzene, but a low content of oxygen-containing molecules such as water and carbon dioxide. This chemical composition is quite different from disks around the stars like the Sun, where oxygen-containing molecules predominate. The presence of these hydrocarbons in such quantities suggests that the material is transported along the disk in a radial direction, affecting the basic composition of the planets that form in it. These differences in chemical composition mean that rocky planets around tiny stars may have different atmospheres than Earth. For example, the primary atmospheres of many of these planets may be dominated by hydrocarbon compounds rather than oxygen-rich gases. This could lead to the formation of carbon-rich planets with atmospheres quite unlike our own. The discovery of such carbon-rich environments is crucial to understanding the possibility of life. On Earth, carbon is the basis of organic chemistry, underpinning DNA, proteins, and other vital molecules. The presence of similar molecules in protoplanetary disks suggests that the building blocks of life may be widespread in the universe, forming naturally during the formation of planets. Moreover, these findings emphasize the dynamic nature of protoplanetary disks and the complex processes that lead to the formation of planets. The imbalance of carbon and oxygen in these disks may be the result of enrichment processes, where solid particles are stripped of their carbon content, releasing it as gas. These carbon-deprived particles form planets with a rocky, carbon-poor body but carbon-dominated atmospheres. The distinction between carbon-rich and oxygen-rich disks is crucial to understanding the potential for life on these planets. Carbon-rich disks, which are dominated by hydrocarbons like ethane, may favor life forms based on different biochemical processes than those on Earth. In contrast, oxygen-rich disks, containing molecules like water and carbon dioxide, are more similar to the conditions that led to the emergence of life on our planet. This chemical diversity means that planets forming in these different environments could have significantly different atmospheres and surface conditions, potentially leading to a wide variety of life forms or prebiotic chemistry that we cannot yet imagine. The discovery of rocky, carbon-rich exoplanets around small stars not only expands our understanding of the diversity of planetary systems, but also strengthens hope for the detection of life beyond Earth. Small stars around which such carbon-rich exoplanets may orbit are abundant in our galaxy. They're often more stable than larger stars and provide a constant habitat for billions of years. This stability makes it more likely that life will have enough time to develop and evolve. But carbon is not the only key element. What else is needed for life? In the search for life beyond our solar system, the concept of a habitable zone, often called the Goldilocks zone, is crucial. There are areas around a star where temperature conditions are optimal for liquid water to exist on the surface of a planet. Liquid water is extremely important because it is a key ingredient, being a solvent and thus providing the complex chemistry required for biological processes. Habitable zones depend on the type and size of the star. In smaller, cooler stars, the habitable zone is closer to the star, while in larger, hotter stars, it's farther away. Finding planets in these zones is a key challenge for astronomers searching for potentially habitable worlds. One state-of-the-art instrument to aid in this search is the Habitable Zone Planet Finder. This instrument, located on the Hobby Eberly Telescope in Texas, is designed to detect exoplanets around low-mass stars by measuring tiny changes in the star's light caused by the gravitational pull of orbiting planets. HPF is particularly good at finding planets in the habitable zones of these stars, which are often dimmer and colder than our Sun. Using the HPF, astronomers have made significant progress in detecting planets where life could potentially exist. By focusing on the low-mass stars that are most common in our galaxy, the instrument increases the chances of finding habitable planets. The high accuracy allows scientists to detect even small Earth-sized planets that might otherwise go undetected. In this context, a very unexpected and intriguing discovery has emerged that calls into question all existing models of solar system formation, shedding new light on the diversity of planetary systems in the universe. The identification of LHS 3154b, an exoplanet that's surprisingly massive for its relatively small host star, suggests there are mechanisms at work in planet formation that we do not yet fully understand. Traditionally, models of planet formation such as core accretion and disk instability dictate that the mass of a star limits the size of planets that can form around it. LHS 3154b, however, does not conform to this rule. Perhaps this planet formed away from its star and migrated inward, or perhaps it was captured from another system. These scenarios shed new light on the formation and evolution of planetary systems. It's particularly remarkable that this exoplanet still retains conditions capable of supporting liquid water. The presence of such a planet suggests that habitable zones may exist in a wider range of conditions than previously thought. However, the presence of such a massive planet in the habitable zone of a small star also has implications for the potential habitability of other planets in the same system. Its gravitational influence can make or break the habitable zone, affecting the climate and geology of all small, potentially habitable planets nearby. This can either stabilize conditions for life or make them more unstable, depending on the characteristics of the system. Interestingly, the unexpected size of the planet brings to mind the evolutionary pathways of planets. It may well represent a stage of planetary evolution that we do not yet fully understand. For example, some gas giants may lose their atmospheres due to intense stellar radiation or gravitational interactions, causing them to shrink in size and mass. This process is known as planetary evaporation or shrinkage. In the context of LHS 3154b, its large mass and unusual orbit suggests that it may be undergoing or has already undergone similar evolutionary processes. The planet may have formed as an even larger gas giant by losing part of its gas envelope or in another part of the stellar system, subsequently migrating under the influence of the host star's dynamic environment. Such discoveries challenge the notion that only Earth-like planets orbiting Sun-like stars can be habitable, and suggest that life can exist in a variety of unexpected environments. As we continue to explore space, the quest to discover and understand exoplanets remains a central focus of astronomical research. Current and future space missions should revolutionize our knowledge of these distant worlds, especially those in habitable zones. One of the key players in this ongoing exploration is the Transiting Exoplanet Survey Satellite. Launched in 2018, TESS is designed to observe the brightest stars near Earth in search of transiting exoplanets. Its mission is to identify thousands of new exoplanets, ranging from Earth-size to gas giants, and provide targets for further study by other telescopes. TESS has already discovered many planets, some of which are in habitable zones of their stars, making them prime candidates for detailed study. The European Space Agency's Ariel Atmospheric Remote Sensing Infrared Exoplanet Large Survey mission, scheduled for launch in 2029, is expected to study the atmospheres of 1,000 exoplanets. By analyzing the chemical composition and thermal properties of these atmospheres, Ariel will help scientists understand the formation and evolution of planetary systems, as well as the potential habitability of these distant worlds. In addition, proposed future missions such as the Louvois and Habex have the potential to take exoplanet research to new heights. The goal of these missions is to directly image exoplanets that are particularly Earth-like and look for signs of habitability with even potential biosigns. By studying the light reflected from these planets, scientists hope to detect biomarkers such as oxygen and methane in their atmospheres. Many exciting developments are looming on the horizon, and they promise to expand our knowledge and inspire further curiosity about the vast cosmos. As we learn more about these distant worlds, the question remains: are we alone in this vast universe, or is life just waiting to be discovered? Beyond the orbit of Mars, among millions of asteroids, the inconspicuous dwarf planet Ceres floats as if to upset the entire cosmic order. Despite its seemingly boring appearance, little Ceres challenged all of cosmology, standing on a par with other planets as the very first dwarf planet known to mankind. But that's not the only thing that has baffled scientists. In a sea of dim meteors, gray Ceres shines like a small star through mysterious bright footprints that may hide cold ocean depths where the heart of life is likely to beat. Today we're traveling with you into the icy depths of the asteroid belt to meet the small planet Ceres, its ocean depths, and its mysterious radiance. So hop on, we'll be there soon. Ceres was first discovered in 1801 by astronomer Giuseppe Piazza. Initially, the scientists assumed that Ceres was a comet, but because of its slow and even motion, like a planet, he revised his calculations and continued observations. Even before the astronomers' research, well-known theorists such as Johannes Lambert had suggested there should be another planet in the gap, or asteroid belt, between Mars and Jupiter given its width. Piazza stopped working on his most significant discovery due to health problems, but his attempts to explore the distant and dark planet and calculate its orbit did not gather dust. Mathematician Friedrich Gauss, using the very limited data that Piazza managed to collect, was able to calculate the approximate orbit of Ceres. In particular, other astronomers such as William Herschel were even able to calculate the diameter, but it was far from reality. The researchers found that the size of the planet was only 160 miles, but in fact, according to modern observations, Ceres' diameter is 584 miles. Giuseppe Piazza considered the object he discovered to be a planet, and yet for 3 centuries Ceres was considered by the wider scientific community as an asteroid. Only in 2006 did the International Astronomical Union finally recognize Ceres as a dwarf planet along with Pluto. The discovery of Ceres could not but leave a mark on modern astronomy. Thanks to the small planet, scientists have deepened their knowledge of how the solar system was born and planets formed. For the first time, we were able to see the embryo of a planet, or planetesimal, so close. Ceres has expanded everything we know about cosmic bodies by its existence, actually forming a new type of planet as a dwarf planet. Due to the difficulties of studying a dim and seemingly dead planet, scientists have long considered it just a large body in the asteroid belt. Its mass is about 25% of all objects in the belt, but still, even dwarf Pluto is 14 times more massive than it. In particular, it seems that due to the gravitational effect of Jupiter, a small planet could not form completely. It is at the embryonic stage, without any opportunity to gain mass from the building asteroids that surround it. It takes 4.6 Earth years to complete a full orbit around the Sun, but its rotation on its axis is only 9 hours, making its day one of the shortest in the solar system. Interestingly, the axis tilt is not visible to the planet at all. It's only 4 degrees, so there's no possibility of feeling seasonal changes on Ceres. The night on the dwarf planet is also absolutely dark because it has no satellites, unlike most other planets, and no rings. Ceres is too small to hold them in its orbit. The planet's 3 times more distant from the Sun than Earth, so the annual average temperature there drops to negative 100 degrees Fahrenheit. Any heat that gets to the surface of Ceres is unlikely to stay there for long. It probably lacks an atmosphere and even a magnetosphere that would protect it from the radiation effects of solar wind. It doesn't seem that such a planet would be able to harbor any life. But pay close attention to the surface of Ceres. Despite its age of 4.5 billion years old, its surface has only a small bunch of craters and no deep impact basin. One could assume the planet could have survived a collision with another massive object that would have broken off a giant chunk of it. But the explanation for this strange phenomenon is different, but no less surprising. In 2015, the Dawn spacecraft went on an expedition to Ceres. The data collected by Dawn showed a rather unexpected result. Having made a complete map of the dwarf planet's surface, Scientists concluded that its surface consists of a mixture of ice and minerals such as clay and carbonates. Therefore, although it is similar to the Earth planet, its density is several times lower. Having studied the smooth surface of the craters, the very unusual bright spots on their bottom, and the furrow patterns across the surface, scientists came to the final conclusion that Ceres is geologically active. What makes its icy surface young again and again are cryovolcanoes. Ceres may consist of 25% water. This water pours out onto the planet's surface, filling deep craters with cryolava. Astronomers have noted that across the planet's surface, you can see rocks, canyons with faults, which may also indicate geological activity, and several dozen cryovolcanoes, with the highest of them being the inactive Ahuna, which is 4 miles high. Ahuna, surprisingly, is a fairly young volcano, having formed about 1 billion years ago, which means that until recently, Ceres had enough heat to form such a geological object. A study by scientists led by paleontologist Maria Cristina de Sanctis found that some volcanoes may still be active, given the bright trail we'll return to later. The activity of these volcanoes is important, not only for the planet's surface, but also for its atmosphere. Due to eruptions or degassing, the atmosphere can be saturated and retain more and more heat. However, Ceres is not a simple case. Its gravity is not strong enough to maintain a permanently dense atmosphere. Instead, Ceres' atmosphere is variable, meaning that it sometimes appears and then disappears. This is all due to solar activity. When the sun heats the ice very strongly, it sublimates, forming a temporary exosphere, and that disappears in a few weeks. At present, scientists working at the European Southern Observatory's Very Large Telescope see no hints of atmospheric recovery shortly. The 57-mile Ocator crater has drawn another serious attention. It was formed 20 million years ago after a likely collision with a very massive object. After the impact, Ceres' crust cracked, releasing much water, which formed long furrows and patterns. The water also washed clay-forming minerals rich in magnesium and ammonium, known as phyllosilicates, to the surface, along with an unusual marine mineral called hydrogolite, and that was found only on Earth. That brings us to another interesting discovery. Ceres may be an oceanic world. Under the icy surface of a dwarf planet, there could be deep subsurface liquid ocean, but that was in the distant past. Now, most likely, the inner ocean is frozen, but not completely. Liquid salty water deposits still exist beneath the surface. Their depth can reach an average of 25 miles, and it's likely that water ice with various gases, such as methane, can make Ceres' crust insulating, thus heating the water internally. Scientist Maria Cristina de Sanctis says that the ocean on Ceres had no reason to exist and should have been frozen by now. But Dawn's research has shown part of it could have survived under the surface. The temperature of these remnants of water can be as low as -22 Fahrenheit, and that's due to the large amount of salt and a mixture of other minerals to stay in a liquid state. According to Dr. Hannah Sizemore, Ceres cannot receive heat from, for example, tidal energy, from orbiting a more massive object like Saturn's moon, Enceladus, and thus keep the entire ocean inside liquid all the time. The impact that formed Ocator became the main driver of cryovolcanism on Ceres, bringing cold water from the ocean to the surface, leaving behind the same strange bright traces that allowed us to confirm the presence of water on the planet. So what are these mysterious marks? At the bottom of Ocator and other craters like Cerealia facula, scientists have noticed large, shiny traces that reflect almost 50 to 60% of all the light that hits them. And the origin of these traces has been puzzling to researchers. At first, the bright spots were thought to be just ice plumes or traces of ammonia or methane, but now scientists are developing another theory. Likely the answer to the mystery of what all these bright spots hide is salt. After cryolava erupts from saltwater reservoirs, the substance gradually evaporates, leaving behind a salt crust containing magnesium sulfate, Epsom salt, and sodium carbonate. In total, the Dawn mission recorded more than 300 such bright areas. Interestingly, however, they all differ. The brightest spots are at the bottom of craters and consist of salt-rich material mixed with water. Another group of bright salt deposits can be found in the form of streaks and patterns diverged from the craters as a result of collisions with meteoric bodies. According to researcher Nathan Stein, over hundreds of millions of years, bright material has mixed with dark material to form the bulk of Ceres' surface. This indicates that billions of years ago, there were many more collisions with the dwarf planet and more than 1,000 bright spots. But why are some spots brighter than others? The process of creating such areas can also be quite specific and unique. For example, there's probably a reservoir of water under a crater, so cryovolcanic activity increases its brightness more intensely. The Seralia Facula crater with a slightly less bright spot could have formed in a more complex way. Cryolava could have moved slowly upward, creating a dome inside which material was boiling all the time until it settled as a mixture of ice and salt pieces on the surface. This whole process of forming bright patches of salt has not yet stopped. Paleontologist Maria De Sanctis has found evidence of traces of sodium chloride in a crater, and after coming to the surface, the water component of this salt should have boiled off within 100 years, but the salt still remains moist. The bright spots again prove the fact of geological activity on Ceres, which is important for the most important process on every planet, the formation of life. As cold and inhospitable as Ceres may be, it meets many of the necessary criteria for the emergence of simple microorganisms and may already have life among its icy layers. Liquid water is the main environment in which life can arise, but of course, to form even an organism's embryo, various chemical elements are needed, the most important of which is carbon. Carbon is used to form the skeleton of living organisms and other crucial chemical compounds. Therefore, knowledge about the composition of the dwarf planet's surface will help answer the question of the possibility of life there. Thus, according to the data collected by Dawn, Ceres' surface contains a lot of silicate and iron rocks, but carbon also makes up a very significant proportion. About 20% of the surface mass consists of organic carbon, which is 5 times more than in carbonaceous chondrite meteorites on Earth. Moreover, the analyzed carbon is mostly mixed with water and clay. Such mixtures, when combined with oxygen and hydrogen, create a variety of organic compounds including sugars, alcohols, and fats. However, this is not the only chemical element important for the development of life that's available on the planet. Water itself already contains a whole range of compounds. Materials on the planet have undergone significant change over billions of years. For example, rocks, such as serpentine and carbonate minerals in the interior of Ceres, melted due to radioactive decay inside the planet, forming rocks similar to shale. The newly formed material probably formed pockets of salty liquid, filling the water with various substances, such as sodium, sulfur, methane, etc. Such a soup of building blocks could be a niche for life, according to geophysicist Mohit Daswani. But more than that, millions of years ago, when there were more collisions and thus the planet received more heat, simple microbial life could hypothetically exist. Therefore, primitive life could probably develop in water tanks right now. However, the problem is still the absence of an atmosphere for a long period of time that would prevent the surface from strong radiation. In particular, the exact amount of liquid water is not known to say for sure that life has a place to form, and in addition, the Dawn mission did not confirm the presence of large amounts of nutrients such as nitrogen or phosphorus, which are necessary for any life activity. Only future missions and soil samples can determine whether Ceres is habitable. In more than 10 years, NASA astronomers plan to send a new expedition to Ceres to collect a sample from the planet's surface. Researcher Dr. Julie Castillo-Roguez says the proximity and low gravity of the planet will allow them to return samples at a relatively low cost. The doctor is confident that there will be organic matter in Ceres salts, which gives us more hope that we can finally find out if we're alone, at least in the solar system. Ceres is an ideal natural laboratory that offers scientists many opportunities to explore the history of our solar system and the origin of life in difficult conditions. Such an intriguing object as the dwarf planet Ceres is of almost unprecedented importance in the study of planetary evolution, and the study of its geological features will allow us to model the entire cycle of planet formation. Future research may be crucial and a breakthrough for all of cosmology. Ceres could hypothetically become one of the first planets on which humanity will find new life. Perhaps this small and inconspicuous dwarf planet will also draw the attention of scientists to dozens of other similar icy oceanic worlds that also have many secrets. Imagine being able to harness the power of the sun, which has been the lifeblood of our planet for billions of years. Its energy, produced in a process known as fusion, illuminates our world and sustains life. But what if we could replicate this process right here on Earth? What if we could create our own miniature suns to power our homes, our cities, and our world? Sounds like science fiction, doesn't it? But what if we told you that this is not a distant dream, but a reality that scientists have been approaching for decades? In the heart of California, at the Lawrence Livermore National Laboratory, a group of dedicated scientists work tirelessly on this mission. Their goal? To accomplish nuclear fusion, a feat that could revolutionize the way energy is produced and pave the way for a future of clean, limitless power. And quite recently, at the end of last year, there was a breakthrough that could have changed everything, illuminating our future. Imagine our star, the Sun, 93 million miles away in the vast expanse of space. It is a giant glowing ball of gas that's incredibly hot. Have you ever wondered what makes the sun shine so bright? The answer is both simple and complex: nuclear fusion. In simple terms, nuclear fusion is the process by which two light atoms combine to form a heavier atom. It's like taking two small Lego blocks and putting them together to make a bigger one. But there's a catch. When these atoms combine, they release a huge amount of energy. They release so much energy that it allows this energy to power the sun and make it shine. Now you may be thinking, that sounds great, but what does that have to do with us here on Earth? Well, if we could replicate this process, we could potentially create a virtually source of clean energy. Imagine your house, your city, and even your car being powered by the same process as the sun. That is what fusion promises us. But this idea is not new at all. Scientists have been dreaming of harnessing the power of fusion for decades. In fact, the concept of nuclear fusion was first introduced in the early 20th century by physicists like Albert Einstein and Hans Bethe. Over the years, there have been many attempts to achieve fusion, from Project Sherwood in the 1950s to the first tokamaks in the 1960s, and the construction of modern facilities such as ITER and the National Ignition Facility in the U.S. Each of these efforts brought us closer to the goal of achieving fusion. Although there have been problems and setbacks along the way, the dream of harnessing star power has never faded. And now, with the recent breakthrough at Lawrence Livermore National Laboratory, we may be closer than ever to making that dream a reality. Just imagine a world in which the light in every house, street, and city is powered not by coal or gas, but by the same process as the stars. As we discussed earlier, fusion is a process in which two light atoms combine to form a heavier atom, releasing huge amounts of energy. But what makes the process so special? Why are scientists around the world so interested in it? Today, most of our electricity comes from burning fossil fuels like coal and gas. These processes release harmful greenhouse gases into the atmosphere, contributing to climate change. Such resources are also finite, which means they will run out sooner or later. But fusion offers another way. Fusion is fueled by hydrogen isotopes such as deuterium and tritium. Deuterium can be extracted from seawater and tritium from lithium, which is abundant in the Earth's crust. This means that the fuel for fusion is almost limitless. And remember, the energy released by fusion is enormous. Just 1 gram of fusion fuel can produce the same amount of energy as 8,000 gallons of gasoline. That's like driving around the Earth more than 300 times. Fusion could generate huge amounts of energy without the carbon emissions associated with fossil fuels. This could help us fight climate change and move towards a more sustainable future. The outlook for fusion energy extends beyond the scientific community. Political figures such as U.S. Senate Majority Leader Charles Schumer also recognizes its potential. He stated, "This breakthrough is a giant leap toward making fusion power a reality. It marks the beginning of a new era in energy production that is cleaner and virtually limitless. The potential for our economy and the environment is enormous." With the stakes so high, it's not surprising that the fusion race is often compared to the space race of the 20th century. But achieving nuclear fusion is not easy. It requires incredibly high temperatures and pressures, such as those found in the heart of the sun. And also on top of this, for many years, the energy required to start a fusion reaction exceeded the energy it produced. But this is where the Lawrence Livermore National Laboratory and the National Ignition Facility come into play. They're working to make fusion a reality, and their recent breakthrough could be a game changer. Imagine a place where the world's brightest minds come together to solve some of the biggest problems facing humanity. That place is the Lawrence Livermore National Laboratory, or LLNL for short. Located in California, LLNL is a center for scientific and technological innovation. It is home to thousands of scientists, engineers, and other professionals who work on a wide range of projects from national security to environmental science to, you guessed it, fusion. One of the gems of LLNL is the National Ignition Facility, or NIF. This is where the magic of fusion happens. NIF is the largest and most powerful laser facility ever built. It is the size of 3 soccer fields and contains 192 laser beams that can transmit more than 2 million joules of energy. 2 million joules is about the kinetic energy of a car driving down an expressway. So imagine the energy of a car rushing down a highway concentrated at a tiny point in a split second. That's the kind of energy we're talking about when the ignition system lasers go off. But what exactly does the NIF do? Its main task is to create extreme states of matter like those found in the cores of stars or inside nuclear weapons. It does this by focusing its 192 laser beams on a tiny target, creating temperatures and pressures that are several times higher than those at the center of the sun. The target is a tiny capsule filled with fusion fuel, which is a mixture of hydrogen isotopes deuterium and tritium. When the lasers strike the target, they detonate the fuel, triggering a fusion reaction. But the road to this point was far from easy, as LLNL Director Dr. Kim Budil says. The quest to ignite fusion in the laboratory is one of the most significant scientific challenges ever undertaken by humankind, and its achievement is a triumph of science, technology, and above all, people. Overcoming this threshold is a vision that's led to 60 years of focused inquiry, a continuous process of learning, building up, expanding knowledge and capabilities, and then finding ways to overcome new problems that arise. These are the problems for which U.S. national laboratories were created. NIF is a marvel of modern technology and science. and it's played an important role in advancing our understanding of nuclear fusion, but it's not just about science. The work being done at NIF may one day lead to a world powered by clean, abundant fusion energy. So how did scientists achieve these results? Let's delve into the details of the achievement and how it brings us one step closer to such a future. In December 2022, something extraordinary happened at the National Ignition Center. For the first time, a man-made device achieved a fusion reaction that produced more energy than was consumed. This is known as fusion ignition, and it's really important. But what exactly does fusion ignition mean? So remember how we talked about fusion like connecting two small Lego blocks to make one bigger? Fusion ignition is similar to that, but with a twist. Instead of just joining two blocks together, you join so many blocks that the energy release starts a chain reaction, causing more and more blocks to join together on their own. It's like lining up a row of dominoes and knocking over the first one. That first knuckle knocks over the second, which knocks over the third, and so on until all the knuckles fall. Well, that's exactly what happened in the NIF experiment. The energy from the lasers triggered a thermonuclear reaction that continued on its own, releasing more energy than it took to trigger it. But achieving this has not been easy. As Dr. Arati Prabhakar, Chief Science and Technology Advisor to the President, says, "We have had a theoretical understanding of fusion for more than a century, but the road from knowledge to action can be long and difficult. Today's milestone shows what we can do with persistence." Once again, as the sun sets, we're left to wonder, what if we could harness the power of the stars to light our cities, power our homes, and grow our industries? But what would a world powered by fusion energy look like? First, fusion energy is clean. Unlike fossil fuels, it produces no greenhouse gases or harmful pollutants. This means it could play a crucial role in combating climate change and improving air quality. In addition, fusion energy is safe. There's no risk of meltdown as in a nuclear fission reactor, and it produces no long-lived radioactive waste. In the event of a malfunction, the reaction simply stops. We have an enormous supply of fusion energy. The fuel for fusion is water and lithium, which is in abundance on Earth. This means that the fusion energy can provide a virtually unlimited supply of energy, reducing our dependence on limited resources like oil and gas. But while the potential benefits of fusion energy are enormous, there's still many problems to be solved. Fusion reactions require extreme conditions that are difficult to achieve and maintain, and the technology to capture and convert fusion reaction energy into usable electricity is still in the early stages of development. However, the event itself gives us grounds for optimism. It shows that fusion ignition is possible and that we are on the right track. Thanks to continuous research and development, the dream of a world powered by fusion energy can become reality. But what does the future hold for fusion energy? Although the recent achievement of fusion ignition is a milestone, it's only the beginning. There's still a long way to go before fusion energy can be used on large scales to power our homes, cities, and industries. Future research will focus on several key areas. First, maintaining the extreme conditions required for fusion reactions is a major challenge. Second, we need to develop the technology to capture and convert the energy produced by these reactions into useful electricity. This will require overcoming numerous technical challenges, from handling the intense heat and radiation produced by the reactions to finding materials that can withstand these conditions for long periods of time. Another important step is to scale up these reactions to a size that could power a city. Designing and building a fusion power plant that could operate continuously and reliably is an important challenge. This applies not only to the fusion reactor itself, but also to the infrastructure for fuel supply, energy capture and conversion, and waste management. However, the potential benefits are enormous. Fusion energy could revolutionize our energy system, providing a virtually unlimited supply of clean and safe energy. It could help us fight climate change, improve air quality, and reduce our dependence on limited resources such as oil and gas. The road to fusion energy is a marathon, not a sprint. It will require continued investment in research and development, cooperation among scientists around the world, and the support of politicians and the public. But still, a promising start has been made. The recent breakthrough at the National Ignition Facility is a beacon of hope, lighting the way toward a future based on clean, abundant energy. And the farther we look into the future, the brighter the prospects for fusion energy shine. One thing is certain: the day will come when star power will no longer be a distant dream, but a reality within our reach. In 2021, the James Webb Space Telescope, or JWST, was launched from Kourou, France, to study at Lagrangian point L2 the cosmic bodies and distant galaxies around us, which can help us learn more about the birth of the universe. Equipped with large mirrors and revolutionary instruments, James Webb was able to make several important discoveries for the scientific world in just 1 year of the mission, including such complex cosmic processes as star formation and their death. Today, you'll learn about JWST's most remarkable discoveries to date, from the first detailed image of a cluster of galaxies to a new exoplanet. One of Webb's first images was of the galaxy cluster SMACS 0723, 4 billion light-years from Earth. It was not a discovery. The cluster was first explored by Hubble. However, thanks to its cameras, Webb was able to provide a very detailed image, revealing to scientists hundreds of previously unseen small galaxies. Interestingly, Webb made this image in just 12 hours, when it would have taken Hubble several weeks. Webb's photos will allow scientists to study young galaxies before they merge into larger spiral galaxies. For example, a study led by Rohan Naidu of Harvard University indicates that some galaxies there may have formed in as little as 300 million years after the Big Bang. In addition, scientists noticed elongated galaxies that also appeared simultaneously in different places. According to the research of astronomer Massimo Pascal, the cause of stretching may be the gravity of the galaxy cluster, which distorted the light, causing galaxies to appear in different places. The scientist also noted the elongation of SMACS 0723. It could be caused by its collision with assumingly another galaxy cluster. The next important image of Webb was a rare ring galaxy, the Cartwheel, 500 million light-years away. It was discovered back in 1941, but a detailed image was only obtained now. Its strange appearance, reminding us of a wooden carriage wheel with a circle in the center and diverging spokes, probably formed as a consequence of a high-speed collision between two galaxies over 400 million years ago. Therefore, it's likely that the Cartwheel galaxy looked just like our Milky Way before the collision. Moreover, Webb discovered that the core of the wheel contains a large amount of hot dust and that the brightest regions emanating from the center contain many young stars. That is, as the galaxy expands, it pushes dust and gas outward, forming stars. The Cartwheel galaxy is still transforming after the collision, so further observations by Webb could reveal more of the mysteries of this galaxy and also look at the star-forming process. In July of 2022, Webb captured the last moments of a dying star that had been emitting gas and dust for several millennia, forming the South Ring Nebula. This nebula, only 2,000 light-years away, was also explored by Hubble, but it only captured one star there, very bright in the infrared. As the emission continued, the star, which was 3 times the size of the Sun, shrank significantly, turning into a white dwarf. Because of this, the star could not shine brightly. Scientists then concluded that all the material ejected by the star must have formed a dust disk, and that would have glowed when heated. Such a dust disk could only be created by another star. Moreover, Webb noticed another oddity. The nebula has lines along its edges. It's unlikely that the dwarf itself could have created such patterns. Thus, Macquarie University astrophysics professor Ursula DeMarco believes that the white dwarf may have several companion stars that scattered all the material and created a disk around the central star. Finally, Webb confirmed that there is a second young star near the dwarf, although no other stars are visible. Scientists speculate that they are either too dim or have already been absorbed by the central star. Therefore, Webb's study will help scientists not only learn more about this association of stars, but also to study the chemical composition of the ejected material. In addition to the death of the star, Webb was able to capture its birth. Webb succeeded in capturing the bright clouds emitted by the newly formed star, L1527, at a distance of about 460 light-years. The star emits layers of dust and gas in different directions, so the appearance of this nebula resembles an hourglass. The color of the clouds is determined by the thickness of the dust, an orange color where the dust is denser and vice versa. The thinner the layer, the bluer the color would be. Scientists estimate that this star is only about 100,000 years old, when a star is formed about 10 million years or more. Also, NASA researchers believe that L1527 is already approaching the generation of its energy through nuclear fission, so it will soon be able to ignite on a cosmic scale. Moreover, the barely visible line that crosses the clouds is a protoplanetary disk, and it is the size of our solar system. Therefore, it is likely that planets could form around L1527, just as in our system. This in turn will not only allow us to observe what the solar system looked like when it formed, but also to consider these exoplanets as possibly inhabited. Another distant Kiel Nebula was the target of James Webb's research. The Kiel Nebula contains a region of star formation NGC 3324, the edge of which Webb captured in detail. The rock-like part of the nebula is actually hot, ionized gas and dust. Amid this nebula, Webb was able to capture with its cameras hundreds of previously hidden newborn stars. Moreover, the telescope also detected thin jets of hydrogen erupting from the top of the nebula. Such columns could probably indicate an active period of star formation. Such an event is very rare, and it lasts only up to 10,000 years. This discovery is a new step in the study of star formation and its effect on nearby planets and the entire nebula. In addition to the Kiel Nebula, Webb studied another nebula that could also bring scientists closer to a better understanding of star formation. The Pillars of Creation Nebula is about 6,500 light-years away in the Eagle constellation. In its huge columns of dust and gas, 4 to 5 light-years long, Webb discerned many young stars that are just forming. Take a look at the nebula's second pillar. The top of it is reddish and looks like lava. This means that there are stars in this area that are emitting jets during formation, which means they are estimated to be 100,000 years old. By the way, scientists also noticed that there should be more stars in this image. The fact is that stars have recently finished their development. They had got rid of the dust surrounding them, so it's difficult to see them in the mid-infrared. But nevertheless, the information from James Webb will be enough to investigate how stars form and emerge from these dust clouds. Webb's next discovery is of even greater interest to scientists. This time it is not a nebula, but the brown dwarf Glass JWST BD1 at a distance of about 2,000 light-years from Earth. Brown dwarfs are quite rare and dim and also have some of the characteristics of a planet. That is, they're not massive enough to synthesize hydrogen and emit starlight, but they also have an atmosphere like a planet, with the probable presence of water molecules in it. So studying why a star has so little mass will help scientists learn more about the boundary between planets and stars, and how they form. Now back to our dwarf. Very little is known about glass JWST BD1 at the moment. It is about 30 times larger than Jupiter and has a temperature of about 720 degrees Fahrenheit. Brown dwarf researchers led by Mario Nannino said that further observations are needed to learn the star's chemical composition and properties. But in addition to glass JWST BD1, Webb was also able to study the previously discovered brown dwarf VHS 1256-1257b, specifically its dust clouds. VHS 1256-1257b is relatively close, 72 light-years away, so Webb was able to examine its atmosphere in detail. It found many important chemical elements there, including water and carbon dioxide, as well as a cloud of silicate particles. Thus, Webb was able to bring scientists a little closer to understanding the structure of dwarfs and exoplanets. The first exoplanet that Webb captured was the gas giant HIP 65426b. This young exoplanet, 385 light-years away, was discovered back in 2017 by a ground-based telescope. However, the study of the planet was complicated because it was quite difficult to get a detailed image with short infrared light waves, especially because of the large number of bright stars. For example, the star HIP 65426, around which the exoplanet orbits, is 10,000 times brighter than it. Nevertheless, Webb's cameras took the first direct image of the exoplanet during its mission. HIP 65426b is 100 times farther away from its parent star, so the telescope was able to spot the planet. Although Webb did not get a closer look at HIP 65426b because of the enormous distance, the images will help scientists learn more about the planet and the system as a whole, as well as opening up the possibility of taking pictures of other distant exoplanets. Another of Webb's first scientific mission targets was the WASP-39b exoplanet. It was previously observed by the Hubble and Spitzer telescopes, but Webb was able to provide an almost complete characterization of its atmosphere. WASP-39b is a gas giant slightly smaller than Jupiter with very low density, so life is unlikely to be possible there. It is about 700 light-years away from us and orbits a G-class star, WASP-39, similar to our Sun, though it's slightly smaller and cooler than our star, probably due to its older age. However, WASP-39b is the closest planet to the central star. It orbits at a distance of 4 million miles or 7 million kilometers, which is 8 times closer than Mercury to the Sun. That's why temperatures there are very high on average, 1600 Fahrenheit, and with its mission, Webb confirmed the presence of water vapor, sodium, and potassium in the atmosphere, which had been detected by previous studies. This year, Webb recorded sulfur dioxide, oxygen, methane, and for the first time on exoplanets, carbon dioxide, which amazed scientists. Sulfur dioxide results from a chemical reaction when it interacts with starlight. And by the way, on Earth, the ozone layer is formed as a result of the same interactions. In addition to the presence of oxygen, according to Kazumas Ono, a scientist at Santa Cruz University, it may indicate that the planet is migrating toward its current orbit. Such reactions have not yet been observed on other exoplanets, so WASP-39b offers scientists an opportunity to study the formation of atmospheres on exoplanets and the history of the formation of the planets themselves. And finally, in January 2023, it was revealed that Webb had been able to join the ranks of discovered exoplanets with its find. At a distance of about 40 light-years from Earth, Webb, observing a red dwarf, noticed how the light from the star covered the object orbiting it. In just 2 rotations or 4 days of the object around the star, Webb accurately determined it was a planet. Thus, exoplanet LHS 475b became the first planet discovered by Webb. Making a direct picture of the planet is not something Webb has had success with yet. However, researchers have already been able to give the first characteristics of LHS 475b. At this time, we know that this exoplanet is almost entirely the size of Earth. It has a rocky composition and has a fairly high temperature of about 100 degrees Celsius more than the Earth. It's not yet been possible to determine whether it has an atmosphere. However, if an atmosphere is detected, a group of scientists led by Jacob Lustig Jaeger believes it could be similar to Venus. Still more research is needed to establish whether there is an atmosphere there and perhaps even whether life could exist there. The James Webb Telescope has reached its research point in a year. Together with the scientists, they've about 9 more years of work ahead. Webb's main missions are the study of early galaxies, star formation, and the in-depth study of exoplanets and planets in our solar system. Shortly, Webb will probably study the TRAPPIST-1 system, some planets of which may be inhabited. Moreover, Webb will focus on studying the atmospheres of Mars, Pluto, Jupiter, and Kuiper Belt objects, which could provide more information about the origin of the solar system. Another mission for Webb is to investigate the sources of water in space objects. To do this, Webb will study Jupiter's icy satellite Ganymede, where there could be an internal ocean. This could also help further studies of icy ocean satellites like Enceladus, Europa, and possibly Mimas. Therefore, we expect that Webb will be able to make many discoveries over the years that will change our understanding of the universe.